Have you ever heard of the Cheshire Cat from Alice in Wonderland? The mysterious cat that disappears, leaving only its grin behind? Well, after Schrodinger's cat had its moment in the spotlight, quantum mechanics found another feline puzzle, the Quantum Cheshire Cat. Just like the Cheshire Cat separates from its smile in the story, quantum experiments appear to show that particles can separate from their properties. In classical reality, this shouldn't be possible, just like a smile floating in mid-air without a face. This strange phenomenon has fascinated physicists over a decade. It's a bit like seeing lightning flash across the sky and then hearing the thunder a few moments later. The two are connected, but they arrive separately to a particular location. In quantum physics, something even stranger happens. A particle like electron or a photon can appear in one place, while its property like its spin or polarization appears somewhere else. Let us consider one of such fascinating properties, the quantum spin. Spin is like a tiny built-in twist in every particle. You can think of it like a miniature gyroscope that always points in certain allowed directions. This spin is intrinsic, meaning it's a part of the particle's very identity. Usually the spin and the particle are inseparable, but thanks to clever quantum experiments, something extraordinary was observed. Why is it worthwhile to know what a spin is? You may have heard of electricity. Electricity harnesses the motion of electrons to power almost everything around us. And learning how to control other properties like spin would allow us to perform logical operations by controlling it. But here's the twist. Until we measure it, the spin can exist in many directions at once, a superposition, and the act of measurement collapses this cloud of possibilities into one specific direction. One such experiment that tried measuring how properties like spin can seem to be separate from the particle is the Quantum Cheshire Cat experiment.
At the heart of the Cheshire Cat experiment is the Mach-Zehnder interferometer. A particle enters a 50-50 beam splitter, which is an optical device that splits one incoming beam of light into two. These two paths later meet at a second beam splitter where there are two outgoing paths into separate detectors. Simply the act of measurement in of itself can alter a particle's state irreversibly, so we leave the detection until the very end. When a quantum state is measured, it probabilistically collapses into one of the possible measurement outcomes. Classically in this setup, you'd expect individual particles running through this interferometer to randomly choose a path, resulting in a 50-50 distribution at the detectors. Quantum mechanically though, this isn't the case. The particle's evolution is governed by its wave function. The wave function allows for superposition so that, in effect, the particle can sample both paths at the same time. Then, it interferes with itself at the second beam splitter, causing it to prefer going to one detector over the other. You can play around with this simulator courtesy of the University of St. Andrews to explore how implementing a phase shift will change the probabilistic outcome. See how for this choice of phase shift, we can always force it to take the bottom path. The Cheshire Cat experiment now involves introducing a second property of a particle. For instance, an electron and its spin. An electron has two possible spins and it has two possible paths it can take. We can now make measurements for a pair of physical properties. Let's call the spins up and down, and let's say all incoming electrons start spin up. On the bottom path, you can add a spin flipper that turns up into down, and at one of the detectors, you can put a filter which only lets spin up through. Therefore, if an electron is detected here, we infer that it took the upper path. In the theory paper, the authors introduced the notion of a weak measurement, where they make small disturbances to one path to try to probe some measurement without destroying the wave function. According to the results of their weak measurement values, the electron goes down one path while the spin takes the other path. Through this technique, it was originally claimed that particles could be detected physically in one location, while their polarization or spin appeared to be measured in another place entirely. This peculiar separation defines the Quantum Cheshire Cat, and people took this idea and ran with it. Okay, this was not universal consensus. Despite a simple experimental setup, the results rekindled a debate about the ontology of quantum measurement. Two operators A and B are said to be compatible if they commute, meaning you can apply them in either order. Operators do not commute in general, meaning you would make measurements in a different basis. This brings us to the rebuttal that came a decade later, which uses context theory to handle the Quantum Cheshire Cat paradox. In this framework, a context is a set of measurements that can be jointly measured, meaning they're compatible. Take for instance this Peres-Mermin square. It consists of a 3x3 set of 2-qubit observables which can take a value of plus or minus 1. Each row and each column contains compatible operators and so define the contexts. When you multiply out these rows or columns, you get the identity except for this last column giving a minus sign. What's truly puzzling about this square is that it's impossible to assign a fixed, well-defined value of plus or minus 1 to each observable a priori. If you multiply out the values of the observables row by row, you get plus 1, but if you go column by column, you get minus 1. This contradiction highlights the contextuality of quantum measurement. There's simply no way to assign fixed, non-contextual values to all 9 observables. And so, like the Cheshire Cat's smile lingering after he vanishes, quantum measurement stubbornly defies us yet again. The setup we were looking at before used incompatible measurements, which muddies the discussion. Instead, the 2023 authors argue from contextuality that the original disembodied property claim isn't sound. Propositions about the physical location and spin of the particles may be true, but not at the same time. The interpretation of the particle going one way and the spin in the other is just one combination of a set of mutually contradictory statements.
If you'd really like to know, he went that way.
Thanks for watching. If you're interested in a career in quantum, or you're interested in quantum software such as Qiskit, find out more information in the description about our Quantum Science and Technology Masters here at Trinity College Dublin.